This lesson is part of Module 2 of the SaferAfrica Road Safety course. The module is focused on data, data collection, data management, data analysis and the relation between data and road safety policy making. The module is based on information from different courses and put together for the EU Safer Africa project. The course will be presented by Martin Narvabi-Niaki and Henk Stipdonk. You will hear our voices mostly, so in case you wonder who you are listening to, we'll introduce ourselves briefly.
On the first day, you will learn why and what type of data are relevant for road safety policy making. The formal definitions will be presented, for example, crashes, deaths, injury severity, safety performance indicators, and the relationship between risk, distance traveled, and the number of casualties. On the second day, we will focus on crash data and their relevant variables, the shortcomings of crash data, and how to handle poor data quality, as well as the possible options to enhance data quality. On the third day, you will learn about the importance of risk factors and key road safety performance indicators, or SPIs. We will talk about how these SPIs are used in connection with road safety measures. On the last day, we focus on data analysis and how to structure fact-based policies from the analyzed data. Here is the outline of today's lecture. In the first part, I will introduce the entire module and today's lesson. In the second part, I will give a brief summary of the types of data that are relevant for road safety research and policy making. The third part is dedicated to all relevant post-crash processes that result in useful data such as police reports, ambulance and hospital records, death certificates, and insurance claims. Finally, I'll present a simple road crash model that connects road crash numbers, distance traveled, and associated risk factors. As an introduction, I would like to briefly discuss the relevant road safety data that is available in your countries. Here we already have the first important issue to discuss. What is relevant data? Of course, we immediately think of the number of road crashes. Can you think of any other relevant data, either available or unavailable in your country? What is your view on the necessity of data for road safety policy making? And what data would be needed for effective policy making? This sheet describes the essentials of the safe system approach. Traveling is unsafe, and the reason is people make errors and disobey the rules. That's why we speak of human behavior, and this is the premise for all effective policies, because we need to understand that this human behavior is not something we can change. This is why air travelers are thoroughly checked by security all over the world, because campaigns and education will not teach people not to take unsafe items on the plane. Similarly, we need a safe system that allows road users to make errors and disobey the rules without them being killed or killing others. The solution lies in adaptation of the traffic system. We need professionals, such as you, to think about improving the safety of the traffic system, while accepting that people make errors and disobey the rules. And so we need road authorities to design and build safer roads and road networks. We need safer vehicles by design, by maintenance, by regulation, and by supervision of vehicle authority. We need enforcement to correct all kinds of excessive behavior, and we need a coherent approach for all of these methods. This course will be about the data that we need in order to get this going and make the right policy choices.
First, let's look at some essential definitions. Here you can see the most common and internationally accepted definitions of road crashes, road deaths, and serious injuries. It's good to know that a crash is not defined by its cause, but by its circumstances and its medical results. And so many single vehicle crashes should be considered a road crash. These internationally accepted definitions should be used. However, if it's not possible in your case, then you should come up with your definitions and stick to it and not change the definition irregularly. In the USA, a motorized vehicle should be present for it to be considered a crash, and crashes with only bicycles and pedestrians are not seen as a road crash. In a country such as the Netherlands, where many people cycle, this makes a big difference. In the Netherlands, there are approximately 80 deaths in single bicycle fall crashes, which is 15% of all fatalities. Another case is when a motorcyclist overlooks a pothole, for example because it is filled with water from the rain, and he falls and breaks his neck. This should also be a case when it is considered as a road crash.
To know where to go in road safety policy making, we need to know something about the actual crashes. In-depth research of typical crashes gives a picture of the variables you need to know about. Once we know about the relevant factors in a typical crash, we can set up a police report system. Police are present at the crash locations and they have authority, so they can collect the most relevant data. Other information can be gathered from ambulance trips, hospital visits, both of which require that the patient was hurt in the road crash, and also from insurance companies, but usually there is very limited value to these data. In some countries, there is a death certificate system for unnatural deaths from which road death numbers can be derived. Travel data is also very important because more travel means more crashes. And some travel properties can increase the probability of a crash. For example, nighttime motorbike riding while drunk is more dangerous than driving a truck while sober on a quiet motorway. And so travel data is needed, and we need them stratified by all kinds of variables such as road, travel mode, time of day, road user age and gender, but actually by other variables that denote risk, such as traveling with or without a helmet, excessive speeding, driving sober or drunk. Travel data can be obtained from surveys, roadside observations, or GPS tracks. These methods cost money, but they do not have to be expensive if people and resources are available. The quality and the accuracy can be an issue with these data, but they can also be improved with implementing the resources. Other possible travel data sources include inventories of the vehicle fleet, driving licenses, vehicle sales, road network length, and population. Anything that can serve as a proxy for travel data is welcome. And always as much as possible stratified by type, whether it's license type, vehicle type, or road type. Other relevant data could be violation data, also stratified by type of violation. Before asking ourselves who should collect the data, consider the question what data we need. The answer depends on the type of crash and what you can do with the facts. So the color of the car would be less interesting than the location of the crash and the age of the driver. We need to know all relevant factors since these can help us avoid future crashes with proper measures. We can make a list of relevant variables using the Hadon matrix. This is what Haddon's matrix looks like. We may fill this matrix while looking at a crash. For example, a motorcyclist drives into a pothole filled with water from an earlier rain shower and breaks his back. Pre-crash variables might be as shown. Here's an exercise. You can consider a relevant crash and try to sum up relevant variables for each of the 9 cells in the matrix. Then compare your results with other students and find variables you agreed upon and also variables that were unique for your crash example. You can pause the video right now and take some time to fill in the cells. In the third part of today's lecture, we will talk about the dynamics of traffic, crashes, and relevant post-crash activities. There are many different types of crashes, and so their report rates or quality may depend on the type of crash. For example, the severity of the crash can be in terms of the severity of the most severely injured, or it can be in terms of the number of victims. There's also a difference between driver and passenger being injured, and also a difference between a single vehicle and multi-vehicle crash. The location of the crash can also influence the quality of the report. A crash can be fatal or non-fatal. If it is a fatal crash, there may be one person who dies or more than one people. And if it is a non-fatal crash, there may be one or more seriously injured. After transferring to a hospital, if the seriously injured individuals die, then that crash would be considered a fatal crash. If a crash is without dead or injured, it is called material damage only or property damage only. The report rate of these crashes may vary depending on the number of injured or deaths. Crashes can be single traveler or multi-traveler. If multi-vehicle, it can be between motor vehicles or between a motor vehicle and a cyclist or a pedestrian. Single vehicle crashes may constitute a substantial component of the crashes. In the Netherlands, 60% of car occupants die in a single vehicle crash, whether hitting a tree, driving into the water, etc. In many countries, these crashes may be overlooked by the police for various reasons. The data that is needed and available may be of a different nature and quality for different types of crashes. In any case, for all people and for all vehicles involved, we need separate records. There can be 2 or more casualties in one vehicle. Drivers may or may not be a casualty themselves. Our crash reports need to allow for information about victims and their vehicles, but also of vehicles without casualties and their drivers, for example, their age, gender, alcohol level, experience, etc. If the victim is a passenger of a vehicle, we also need to know variables regarding the driver, whether it's a bus driver, taxi driver, passenger car driver, or a motorcycle driver. For example, did the passenger wear a helmet or a seat belt? Or was the passenger standing in the back of the truck or a bus? The accuracy of the reports may depend on the complexity of the crash scenario and the ease with which to gather this information. Last but not least, in many countries, not only Asia or Africa, but this could well be true in European or American countries, the report rate depends on the location of the crash. The nearer to important towns, the better the report rate. Be aware of this when performing road crash analysis and see if you can prevent this bias. In this exercise, you are asked to think of reasons why single vehicle crashes or urban and rural crashes are differently reported and are of a different nature. What could this mean for your police report database and for the analysis you carry out? Would that be a problem or not? Take a few minutes to think about this.
This part of Lesson 1 focuses on a simple road safety model. You will not need excellent mathematical skills to understand the model, but yes, it does contain a mathematical formula. The model I will present is actually very simple conceptually. it can be used to derive an inventory of the necessary data. Everything about road safety starts with distance traveled. Suppose we want to travel from Abidjan to Laos. Like that. More than 1,000 kilometers across 5 countries: Ivory Coast, Ghana, Togo, Benin and Nigeria. The safety of this trip depends on the properties of this trip. If we go by truck, our chance to survive is different from that of traveling by a motorcycle. Safety belt or helmet use matters. Speed matters. The safety quality of the road matters. The time of day matters. So all those factors determine the risk of the trip. Some of these factors can be influenced by the traveler in principle. He may choose to travel during daytime only. He may choose the speed and the travel mode. But the road, however, is beyond his scope of choice, although he might choose between different routes. Now, the safety performance indicators, or SPIs, determine the factors that matter. So SPIs are always properties of sections of the trip. And they should be expressed as a proportion of distance traveled, and we need to choose the right SPIs in our plans. Essentially, the number of road deaths is proportional to distance traveled, assuming all other factors being equal. If there are twice as many 35-year-old motorcycle riders as compared to 30-year-old motorcycle riders, one would expect twice as many deaths among those 35-year-old as compared to the 30-year-old. Well, provided of course that both are equally well skilled riders, ride during the same time of day and on the same roads, etc. So roads, driving skills, time of day, these are all factors that may influence the riding risk. And there are many other factors, all properties of the trips. High risk yields higher number of road deaths and high distance as well. Of course, a high volume of low risk may yield equally many road deaths as a low volume of high risk. Therefore, to understand how the number of road deaths depend on travel, we need to know the amount of travel, M, and its risk, R. And of course, the risk actually varies with trip variables. So actually, the total number of road deaths is a sum of many different groups of travel and their corresponding risk. For the Netherlands, lots of those data are available. Now, this formula indicates that risk can be defined as deaths per distance traveled. So risk is deaths divided by distance traveled, where risk is expressed as death per kilometer, or death per mile, or death per billion kilometer, whatever. Mark that risk is tightly connected to distance traveled. We cannot calculate the two separately. Of course, if we know the number of deaths and we know total distance traveled, we can calculate risk. But this risk is an average over a virtually infinite set of pieces of trips, all with very different risks dependent on the properties of each piece of trip. We could also calculate the risk for different groups of travel, for example the risk for car drivers or the risk for motorcycle riders, or we can distinguish different age groups. All this requires data on numbers of road deaths as well as data on distance traveled for the relevant groups, separated. Here are some examples from the Dutch road safety situation between 2010 and 2014, a 5-year average. It shows distance traveled, number of people killed and risk for 4 travel modes and 9 age groups, so it's a rather complex graph. The graph shows average risk as a function of travel mode and age. To construct this graph we need road death data by age and travel mode and distance travel data by age and travel mode. Horizontally we see average annual distance traveled over here in billion kilometers, so a total distance traveled of 5 billion kilometers by pedestrians and 15 in total billion kilometers traveled by bicycle, and so on. And vertically we see average risk in death per billion kilometers. So over here is average risk in billion kilometers, and the data over here are the average for all age groups. Each bar has a horizontal width equal to the distance traveled for each age group. So for example, this width corresponds to the distance traveled in the age group of people of between 20 and 29 years of age. And the vertical height corresponds to the risk for this age group. The area, distance times risk of each bar, equals the number of road deaths for that age group. You remember the formula presented in the last sheet. Number of crashes is risk times distance traveled. As you can see, the differences between average risk are substantial. For powered two-wheelers it's highest, for cyclists and pedestrians it's well, in between, and for cars it's much less. Further, for each travel mode the risk is different for different age groups, and as you can see the risks are highest for the highest age group, because people in this age group are more vulnerable. Not shown in this graph is the risk for a serious injury. These graphs are almost alike, but there are two differences. One is obvious: the risks to get to have a serious injury are of course higher than the risks to get killed. But there's another difference. Perhaps you'd have an idea. But well, I'll tell you right now, the risks to get a serious injury for children is a lot higher than the risk to get killed, and that's because children are not very vulnerable. They survive many crashes, so they have a high crash rate but not a very high death rate. You should bear in mind that if you want to make those graphs, you need to collect all these data and to find out how risk relates to travel modes and age in your country. If you don't have the data, you may assume that it is likely that in your country the differences between age groups and the differences between travel modes of risk may be alike the risks shown in this graph. Now it's time for a small exercise. We suggest that you look at those graphs and think about it some more. What can you see there? And well, in a minute we'll discuss the results. We suggest that you now pause the video for a few moments. As you can see from the graphs, the highest risks are for the people with highest age, 80 or over. But fortunately, their distance traveled is very small, especially for the high-risk power two-wheelers. We hardly have any people over the age of 80 who are traveling on a power two-wheeler, which is fortunate because their risk is really very extremely high. Then we see children in traffic. They're quite well protected in the Netherlands, and especially when they're inside a car, as you can see here, they have a very low risk, especially as compared to the car occupants between 15 and 30. They have a rather high risk, which is much more pronunciated for car as it is for pedestrians or cyclists. And then we see quite a low risk for the 30 to 60 year old, well, for all travel modes actually, and then it's increasing for 60 plus. Now a final word about terminology. We often hear the word exposure, and exposure is used to indicate distance traveled. Personally, I very much am in favor of the word distance traveled when you mean distance traveled, and that is because many road travelers are not actually exposed to risk, but they carry the risk. For example, someone who is a driver who is drunk isn't exposed to a higher risk. He causes this risk. And also, the word exposure is sort of a vague word. It could mean anything. It could mean population or fleet or road length or vehicle size. I don't know. And for every new choice, it means if you change the meaning of the word exposure, you immediately change the meaning of the word risk. I don't like that. So I suggest that when we mean distance traveled, we say distance traveled and not exposure. Now, the final exercise for this lesson, it invites you to think about travel and risk. First, think about the most common ways of travel in your country, and then denote the corresponding risk factors. So, and finally, think of ways your government could improve safety with the safe system measures to improve safe. And remember, we need measures that will last. So change the infrastructure, change enforcement, regulations regarding vehicle use. So we don't like to see statements as people should be more careful. Being more careful is not a measure, it's just a wish. We end day 1 with a homework assignment. It's meant to help you prepare a road safety action plan based on the subjects discussed in this lecture. You can take your time. The result will not be discussed because of the nature of this course. However, if you have the opportunity to discuss the results of this homework with other students, you might give each other some feedback. And if a local teacher is present, results can be discussed with this teacher as well. Thank you.